Welcome to this first multi-phase flow session. There are 4 of us on this panel. There will be 3 presentations, 15 minutes each. And the first person to present will be Norbert Weber, who is currently I'll start the other way around, who's completed his PhD at Technical University of Dresden in Germany as a mechanical engineer. And he's currently working for approximately 10 years in the numerical simulation of electromechanical devices, such as fuel cells and liquid metal batteries. I'll introduce all before we move on. The next person who will be presenting today is Dragana Dimitrijevic, and forgive me if I'm mispronounce this. Dragana is conducting a PhD research in TU Wien in Vienna, Austria, and her interest is in flow separation using centrifugal devices, using their multi-phase flow solvers. The last person who will be presenting is Daniel D Singh. Daniel has completed a PhD at TU Darmstadt and is working as a software engineer for a number of years at NGIS. I hope that's the correct pronunciation as well. So we will be starting now with Norbert, or Dr. Norbert Weber. And his presentation's title is a drift flux, sorry, apologies, the wrong presentation. Local short circuits in liquid metal batteries, influence of the contact angle on the droplet movement in the WOF simulations. So Norbert, thank you very much for joining us. I'll just remind you very briefly that we have 10 minutes for the presentation and 5 minutes for the Q&A following this.
Yes, thank you very much for the introduction. I hope that everyone can hear me. What I will present today, this was basically done by a student of us, Sabrina Bernard. So she's French and she spent 1 year in Dresden working on the simulation of such so-called liquid metal batteries. Now she's back to Paris and doing her PhD at the moment. Liquid metal batteries are meant as stationary energy storage. To build such a cell, you basically take one very heavy metal, put it in some recipient, and then you add an electrolyte, so some kind of salt, and finally a second metal, a light metal. And if you melt all these things, the 3 phases, they will float one above each other, as shown on the right-hand side. One very famous example is the lithium bismuth cell. So in general, you can use many different materials, many metals, many salts, but lithium bismuth is probably best explored. And what happens here when you discharge the cell is simply that the lithium is giving away 1 electron, and then the ion can go through the electrolyte layer downwards to alloy with the bismuth. So it's really a simple alloying cell. The voltage comes simply from alloying 1 metal with the other. And this is also the reason why the cell voltage is fairly low. So usually it's in the order of 1 volt. Here you can see one cell which we built in our laboratory in Dresden. So that's again lithium bismuth, and this cell worked at around 450 degrees and always in the glove box, so under a protective argon atmosphere. What you see, what looks like a little bit like honey, this is the electrolyte, so it's really transparent like water. And on the bottom, just below, is the bismuth. And the droplet, which is now unfortunately not moving, this is a lithium. And when you now discharge this battery, then this droplet will get smaller because the lithium goes down. And when you charge again, the droplet will grow in size and will get larger again because the lithium is transferred from the bottom to the top. In most of these experiments, which I have shown, were really performed inside the glove box with open cells, so that you can look inside, that you can see the flow, that you really can see what happens. And at the beginning, we used as current collector for this lithium on the top simply a metal wire, what you can see on the left-hand side on the top. And what happens there often is that we do not get a really good wetting. So this means the lithium does not attach to the wire, but it forms some kind of bubbles. And these bubbles, of course, they go inside the electrolyte. And if they get too large, we might really get a short circuit from this wire until or up to the bismuth, and lithium might be transferred. This is, of course, not a commercial cell. In commercial cell, we would rather use for the electrode on the top something like what you can see on the right-hand side. So this is basically a metal foam made of iron nickel alloy with large pores, and the lithium goes then inside these pores. And there again, a good wetting is of course very important. We used such foams, we built such batteries, and after freezing the cell, we took them outside, and then we observed what you can see on the left-hand side on the bottom. This spot which is marked by some circle. This is basically an intermetallic phase. So this consists of 75% lithium and 25% bismuth. And the problem is, generally, there shouldn't be any bismuth at this foam because the bismuth should always stay somehow on the bottom of the battery. So it is somehow clear that we had here some short circuit, and it's not a short circuit of the complete cell, but it is really somehow a localized short circuit at a small spot. And when we charged the battery and discharged it, you see it here on the right-hand side, first charge, then some resting time, some discharge. When we did this, we also observed some very sudden drops of the cell voltage. In this inset there, you can see it, and this happens very suddenly in a very short time. And for us, the only explanation is that there was suddenly some amount of lithium transferred from the top to the bottom. And as this happens always somehow under this spiral or under the foam, we cannot observe it visually, but we think that it might be possible that some bubbles formed just below of this foam because of insufficient wetting, and this bubble was then transferred to the bismuth phase. And this was of course driven, this can of course be driven by the Lorentz forces, by a pinching force, by the current which goes through these bubbles. And this is basically the motivation for the simulations we performed. So we basically took the same batteries, the same model, and did a simulation with OpenFOAM. So we said the lithium is a solid. We assumed that the foam is basically a solid, and then we put a small droplet of lithium just below of this foam into the molten salt. We switched on the simulation then to see whether this droplet really gets transferred to the bottom or whether it might swim up. And yeah, we basically used lithium bismuth 550 degrees, exactly as in the experiments to compare it, to be able to compare it somehow. For these simulations, we simply used multiphase interfoam, but we added also the solid region of the foam on the top. We solve, as usual, the Navier-Stokes equation, we solve the phase fractions and so on. But in order to get the Lorentz force, we also need the electric potential, and this we get by solving a Poisson equation. And here, not only in the fluid region, but in the complete geometry, so including the metal foam. Having the potential, we can get the current density easily by the gradient, and we need then also the magnetic field, which we compute in our case by solving a Poisson equation in the complete area. For validation, we thought a lot, and in the end we decided simply to model one single droplet on a surface, because the droplet shape of a droplet on a surface is well known, is described as a Young Laplace equation analytically, almost analytically, and we used this for comparison. So we modeled a simple droplet with 90-degree contact angle, and we got here an error which is smaller than 3%. And at least for us, this was sufficient. Here, I would like to present you some results which we obtained. So everything what was done here was axisymmetric. The top, the metal foam on the top is not illustrated. So basically, in some light gray, you see the droplet, how it behaves over the time. And on the left-hand side, this was really a large droplet. So we first initialized it, switched on the gravity only, so that it gets some steady shape, and then we switched on additionally the Lorentz force, or the current basically. Gravity simply is moving the droplet to the top. But if we have a Lorentz force, or if we have a current, then most of this current will go through the droplet, simply because this lithium has a very high electric conductivity. So this means the conductivity of the lithium is 10,000 times higher of the molten salt. So a lot of current goes through the droplet, and this leads to some force from the sides. So it's basically pinching the droplet, pressing it together. At the same time, the gravity is pushing it upwards. So what we get is some oscillation. And this oscillation, or basically the distance between droplet and bismuth is dark gray on the bottom. So this distance you see in the diagram in the middle. So under certain cases, it really happens that the droplet starts to oscillate, and finally, after some time, maybe even after 1 second, you get a short circuit. And you see there's, you see a few images, how this droplet behaves, how it oscillates, and then in the end, after only 0.3 seconds, we get like a metal tunnel from the metal foam on the top down to the bismuth. And I think this might be what happened in the experiments which I have shown at the beginning. We did then the same experiment on the right-hand side, or the same simulation, but with a smaller droplet. And here it's basically the same thing what happens, but the difference is you need more current to detach the droplet, and it can also happen that you do not get like a metal connection from top to bottom, but it happens rather that a small droplet is cut off and moves, let's say, alone or separate through the electrolyte, and then goes down into the bismuth layer. And all this happens in a very short time, so in only 0.1 seconds. Another interesting thing what might appear is a static or a static droplet shape, but which is not the original shape, a shape which is, let's say, deformed by the Lorentz force. And these things basically happen if we have a quite high current, but which is just below the threshold for a droplet cutoff. So what happens here is basically that the Lorentz force is pinching the droplet, so it's pressing from the sides and elongating the drop downwards and getting it basically nearer and nearer to the bismuth phase. All this what I told you seemed to be very easy, but in the end it was not. There were some challenges which we faced. The first thing is we did everything axisymmetric, but this is of course not always correct, as you can see on the top. The second thing is when we did it in 3D, we put the droplet sometimes in the middle on the top, but then it was moving somehow to the rim of the cylinder. And this does of course not work. And the third big problem was, even if we had no Lorentz force, we already observed oscillations of the droplet, oscillations forever, which never ended. And what we did here first was increasing viscosity to dampen it, but that's of course not very correct. So the second step was then to smooth the interface, and this helped us to improve the interaction between the curvature basically and the contact angle, and this removes then the oscillations. Yeah, with that I'm at the end, and I would like to thank you for your attention, and would like to stress that liquid metal batteries are really an interesting topic for fluid dynamic simulations and quite promising for stationary energy storage, but even such simple things are sometimes not so easy to simulate. Thank you.
Thank you very much, Norbert. We have, sorry, there's a bit of feedback. Would you be able to mute while I ask the question? Okay, thank you. We have little time. We're already 29 minutes from the end. So I'm just going to ask one of the two questions and ask the Holger if he could put his question in the discussion forum so that Norbert has a chance to answer afterwards. The first question was about the use of 90-degree contact angle as a boundary condition for the phase or the interface. How realistic is that for molten lithium on your surfaces?
This depends not only on the lithium, but it depends also on the impurities and on the shape of the metal foam. I think any boundary or any contact angle would somehow be realistic, because we have so many dirty things in the battery. You never know how the wetting is. It changes from day to day. So we use 90 degrees because it's the most simple.
Okay, thank you very much. And apologies for cutting short there. I'm going to have to move on to Dragana. If you wouldn't mind showing your presentation, the title is Modeling of Liquid Separation in a Centrifugal Device using the earlier multiphase solver, two-phase earlier form. Thank you very much.
I hope you can see my screen. So hello everyone, my name is Dragana Dimitrijević, and today I will present you my work on the topic modeling of separation in centrifugal device with an Euler multiphase model with a two-phase Euler foam. So my background is in mechanical engineering, as I finished my bachelor and master at Faculty of Mechanical Engineering at University of Belgrade in Serbia. And right now I am doctoral candidate at Technical University of Vienna in Austria. So, did I switch to second screen or not yet? Okay, perfect. So, within the project I work on, my task was to develop some concept for separation of two liquid phases. After project requests review and detailed research on given topic, I decided to go for an application of centrifugal force in order to separate phases. Main reason was ability to handle liquid phases of low density difference and those with a tendency to emulsify. Design criteria were volume flow in range of milliliters per minute, multi-phase flow consisting of two phases, and separation time of few minutes or less. So device was designed for both offline and online application. So very shortly about centrifugal separation here. So in order to separate phases in one system, the application of centrifugal force appeared to have a significant impact. So this application has a big advantage in variation of centrifugal force strength that can be achieved through change of rotational speed or dimensions of equipment. The research in this direction showed that devices for such operation do exist in a big scale. However, the goal of my study was to develop a system for separation of two liquid phases, where one is water and second is cyclohexane in a lab scale device. Such a device is not known, so new concepts had to be developed. Okay, so experiments were done for design prototype. Mixture was prepared in 10:1 volume ratio of water to cyclohexane. Mixture was mixed with a hand mixer for 1.5 minutes, 2 times 45 seconds, and total amount of prepared mixture was 400 milliliters. Process was pumping the mixture to the system with pump connected to power supply. Control of mixture pumping was achieved with bypass system and valve adjustment. The system was run with motor and sampling was done. After the experiments were done, system was cleaned and dried. So, conclusions after experiments, clear separation was visible as one outlet consists pure phase, only one phase, and other outlet was consisting a mixture. In the table 1 is shown the data, so amounts of each phase at each outlet. So this concept is still in developing phase and more improvement is possible. This will be achieved through computational fluid dynamics CFD methods and design modification with additional experiments. For the simulation of this process, this multi-phase separation will be used CFD software OpenFOAM. Initial and boundary conditions are presented in table 2. Solver that will be used is two-phase Euler form. Calculated Reynolds number is 120, and the flow to be simulated consists of two liquid phases, one being continuous and other dispersed. On the figure here is given mesh representation with approximately 40,000 cells. As mentioned, the solver that will be used is two-phase Euler form, a multi-phase solver of CFD toolbox OpenFOAM. The model that will be used is Euler-Euler model. This is two-fluid model where both phases are described using Eulerian conservation equations. The phases are treated as interpenetrating continuum. They are interpenetrating each other, and they are represented by average conservation equations. The process of averaging introduces to the set of equations the phase fraction alpha. For this simulation is used OpenFOAM version 7. On this slide, I show the velocity fields in various directions. The results are presented with the pictures exported from ParaView. Here is presented alpha field, phase fraction. The phase fraction is defined as probability that a certain phase is present at a certain point in space and time. My results are giving me a physical correction. The result that was somehow desired, as the light phase sticks to X of rotation and heavy phase goes closer to the walls. Results from a simulation. Results are simulated flow consists of two liquids, water and cyclohexane. Mixture is defined to have cyclohexane share at 10% from total flow introduced at inlet. The same amount is expected at outlet. Due to complexity of the system, the simulation results right now are evaluated completely for one outlet setup. It is achieved successfully to obtain the almost exact amount of cyclohexane at outlet, and in the future, or better to say it is in work at the moment, is to obtain all 10% of this phase. So next to this, I plan to do a mesh study with one coarser and one finer mesh, then to try to get stable two outlet simulation, and I plan conference paper, which I already started to work on. Here, I would like to thank to the audience. If you have some questions, and if we have time, you can ask me now, or you can reach me with my email address. I would like also to thank to my team, to financial support from my project, and to all those who are involved in organization of OpenFOAM Workshop 16. So, should I stop sharing my screen?
Hi, Dragana. You can leave your screen. It may prove useful in answering questions, so I think it's good to have it up there.
Just a second. Okay.
And so we do have two questions. The first one was from Kent Wadel, who mentions separation predicted in two-phase Euler form is dependent on drag assumptions between phases. And Kent is asking you what you assumed in terms of predicting the drag.
Yeah, okay. So for this question, I kind of avoided this setup since I know that this simulation that I have is my camera on. I will try to improve, because in real life, as I showed at the first slide from design, I need 2 outlets. Since I couldn't achieve this simulation, I used the simplest setups that I could to get only 1 inlet, 1 outlet. So basically, this is something that this setup for my case are valid for right now, but in future I need to really invest more time for this drag force.
Okay, thank you. There's another question. Abdul Azad mentions this nice presentation and is asking which solver you used. I'll let you answer that, and also what type of mesh you used.
Okay, solver that I'm using is two-phase Euler foam from OpenFOAM 7 version. In 8, it is modified to multiphase Euler foam or something like that, which is improved of two-phase Euler foam, and mesh was done with snappy hex mesh. For background mesh, I used block mesh, and after that I used STL geometries to create final mesh with the snappy hex mesh.
Okay, thank you. And then Olga Marshall mentions all these approaches assume immiscible phases. Is this appropriate for water cyclohexane or cyclohexane, sorry?
Hopefully, yes, because I'm going in this direction. It is for immiscible phases, and mixing of water and cyclohexane showed me that from experiments that they create emulsion, but I found from literature that it is possible to be simulated with this solver, with two-phase Euler foam.
Okay, thank you very much, Dragana. We do have 2 more minutes well. If there is any other questions. Axel Dorian P. Toko is asking you, considering thermodynamics condition may change the results, right? So just looking for confirmation whether you think that thermodynamics condition will change the results. There's a follow-on question, which is your project similar to flash calculation?
I would say no, but I'm not so sure. So considering thermodynamics conditions may change the results. Yes, they can change, of course. And is project similar? I would say no. But as I said, I did only these preliminary simulations, which are somehow valid compared to experiments. But in the future, I would need to set up a more complex simulation where I would have 2 outlets, fully rotating geometry. So for right now, I think no, it's not similar.
Okay. Well, I think it would be probably prudent to move on to the next presentation. So thank you very much, Dragana. And just a final comment from Holger, nice topic, nice work. So thank you, Dragana.
Thank you very much, and thank you to all audience. Thank you.
So the last presentation is from Daniel D Singh from NGIS. And the title of the presentation is a drift flux-based method for wastewater treatment applications. We do have the 10 minutes and 5 minutes for questions. So thank you very much, Daniel, and good luck. You may be muted, Daniel, just to let you know.
Can you hear me?
Yes, we can hear you now.
Oh, good. For some reason I was muted. Yeah, I'm sorry for that. Yeah, my name is Daniel D Singh. I'm software developer at NGIS, where I'm mainly responsible for development regarding multiphase flows. This work has been done with my co-workers, Chris Robinson from CR Technologies and Francis Jacobson from Engis Australia. My talk is titled A Drift Flux-Based Method for Wastewater Treatment Applications. First, why is wastewater treatment important? This has environmental, health, and sustainability reasons. Wastewater causes oxygen deprivation while the waste is decaying, which destroys the plant and animal life in the water. This is also known as biological oxygen demand, or short BOD, and regulations exist about how much discharge into, for example, rivers is allowed. Further, health aspect. Bacteria in the wastewater cause diseases, very simple. Lastly, due to overall water scarcity, careful water management becomes important, which necessitates wastewater treatment. Now, how does wastewater treatment work? There are multiple steps involved. In the primary step, first screening is employed, which is basically just steel nets. This is supposed to remove the largest solids materials that could cause damage to process equipment or contaminate waterways. In the grit removal step, fine but heavy materials such as sand and gravel are removed from the wastewater. In the primary settling tanks, which are large circular tanks called clarifiers, you can see a picture here, the primary sludge containing the faster settling solids is pumped off the bottom of the tank, and the wastewater exits the tank from the top over the surrounding weir. The next step consists of the activated sludge plants, in which the wastewater receives most of its treatment. In anoxic tanks, mainly nitrogen removal is performed. In aeration lanes, we see here, through biological degradation, the pollutants are consumed by microorganisms. In sequential batch reactors, you can see a picture here, are employed also to reduce the organic matter content. In the final settling tanks, which are again large circular tanks called secondary clarifiers, we can see the picture here. The treated wastewater is separated from the biomaterials, which is the activated sludge coming from the aeration lanes. The activated sludge is continuously pumped from the bottom of the clarifiers back into the aeration lanes, and the clear water flows over the weir. Now let us get to the methodology employed in the numerical simulation of settling applications. The flow characteristics are dispersed flows in water at low particle loads and low settling velocities. The modeling aims at design and assurance and optimization, and in general, the main aim is to assess solid settleability. Available numerical methods for this type of applications are naturally Lagrangian particle tracking and Euler-Euler methods. However, there's also the drift flux-based methods in which the relative velocity between particle and fluid are explicitly specified. This has two main benefits. First, it boasts a fast computation time compared to the more complex methods. This is very important as the involved processes are timed in hours and even days. And second, it also has good accuracy since the specified drift flux is based on directly on experimental data. So how does a drift flux-based method work? First, the numerical model and its implementation is based on the interFOAM algorithm. We see here the set of governing equations. The advection of the phase fraction has two additional terms. One is due to the additional settling flux, and the other describes turbulent dispersion. The momentum equation gets an additional drift flux term, which however is negligible in the considered range of applications. And finally, the pressure equation ensures the divergence-free field. However, you should note that the set of equations is formulated exactly like interFOAM, so the barocentric velocity and the volumetric velocity are used interchangeably. As such, the model in this form is actually inconsistent, leading to model limitations. Mainly, the numerical model is only valid for either equal density flows or flows of low solid loads and drift velocity. In the here considered range of applications, however, the second condition is fulfilled. Here, I'm going to briefly introduce the modifications done in the existing drift flux form solver. First, the base solver is unstable due to the way the drift flux is discretized. The employed discretization also inherently leads to a bad estimate of the flux of the face-centered drift flux. Thus, a dedicated new discretization scheme based on a local donor-acceptor consideration has been developed that takes into account the sign of the change in drift velocity with respect to alpha, as well as the drift flux direction. In addition, new drift velocity and mixture viscosity models have been implemented. And as a further step, a multi-species formulation has been adapted. With this, settlability of solids distributions can be modeled, which is important, for example, to simulate primary settling tanks. With this, we come to the applications part. In the first case, taken from the PhD thesis of Bert, a comparison between CFD results and the reported results from the Crofton trial experiments is performed. The case is a final settling tank with about 1 milliliter volume. The inlet is located near the center and is injecting wastewater in circumferential direction with counter swirl, as you can see here in this picture, showing 2 of those inlets. The geometry is simplified into a wedge with 2 inlets of counter swirl. We see here the set of parameters used, where the SSVI, short for stirred sludge volume index, value is used to fix the drift flux model parameter. Now, to explain the process, the wastewater flows in through the inlets, and the activated sludge gets withdrawn here at the RAS outlet, while the cleaned water flows out over the weir. Coming to the results, we compare the concentration profiles over the tank height at different radii measured from the water surface downwards. We can see that the overall agreement between experimental and CFD results is quite good, even though the geometry was simplified for the CFD analysis. As to be expected, in the first sector, which is located inside the well buffer, the comparison is not as good, because there the effects of the actual inlet shape on the flow are largest since it's close to the inlet. Overall, we can conclude that the employed method is suitable for CFD analysis of settling tanks. The employed method is both sufficiently accurate and numerically fast enough for this type of application. In the second case, we look at a primary settling tank of about 5 milliliter per volume. 5 milliliter volume, sorry. Here, compared to the FST from before, we still have a wide particle size distribution with lots of comparatively heavy, fast settling particles. As such, unlike in the FST, a very thin sludge layer of a few millimeters height will typically form on the tank bottom, which is continuously scraped off the floor by the rotating scrapers. At periodic intervals, the settled primary sludge is pumped out from in front of the scrapers through the pipes. This CFD analysis is performed using the multi-species settling solver, considering of a distribution of 9 different particle sizes with different drift velocities. The simulation is carried out using a single reference frame, so the whole tank is rotating. The model process cycle is shown here. For the first hour, both inflow and sludge withdrawal are turned off, and thus the solids settle down with the fluid at rest. After that, the inflow is turned on, and repeatedly, sludge is withdrawn continuously for 20 minutes every hour. So 20 minutes of sludge withdrawal followed by 40 minutes without. In total, 4 such cycles are simulated, as the results have proven this to be sufficient to reach a quasi-steady state. Here we see the animation of the thresholds of solids above 6% dry solids content, meaning for alpha greater than 0.06. we can see at first a sludge blanket builds up, which then periodically reduces during sludge withdrawal and rebuilds over the periods where the withdrawal is turned off. It can be visually seen that the sludge blanket quickly, after roughly 3 cycles, reaches a quasi-steady state behavior. This is an actual tank under operation for which the client wanted to know if there are any chances of continuously sludge built up on the floor, as well as estimate the solids retention coefficient for several flow scenarios and design adjustments. And the CFD results well matched the observed tank performance. With this, I would like to close my talk with a summary and some take-home messages. First, wastewater treatment is of great importance to both the environment, plant and animal life, as well as directly to human health. Due to the ever-growing population, even existing treatment plants are continuously undergoing further development and optimization, thus increasing the demand for numerical analysis. Drift flux-based methods have proven to be well suited for the numerical modeling of a majority of the relevant processes during wastewater treatment. And improvement on the existing framework have been made regarding the numerics, and further a multi-species framework with additional material models has been added. Thank you very much for the talk, for the attendance, and are there any questions?
Thank you very much. Sorry, I've lost your name. Daniel, is it? Yeah, sorry. We have a number of questions, including one from myself. But I'll start with Olga Marshall. He says, thanks for pointing out the inconsistency regarding the barycentric and volumetric mixture velocities both used. Have you used the drift flux for closure of the phase relative velocity?
Well, I mean, yeah, it uses I mean, the drift flux is inherently given, and I'm using the formulation as is. I'm currently also testing the correct formulation, which would be either using the barycentric velocity throughout, getting you an additional pressure term in the pressure equation, and also using the volumetric velocity, so formulating the momentum equation in terms of the volumetric velocity, which gives additional drift flux terms. I've tested both, so yes, they're taken into account fully.
Okay, so thank you very much. The second point there is just, well, to thank you and to highlight that it's an impressive multi-scale modeling and numerics work there. So my own question is, well, I find it impressive as well, and I just wanted you to clarify what type of mesh you used. In particular, I was interested in knowing the computational cost, essentially how many cells and how long it took you to solve the second application that
exactly, yeah. The first one is easy, yeah. The second one, so well, it's our in-house mesher, so it's basically the further development from Snappy hex mesh, Helix hex mesh. So the mesh consists roughly of 20 million cells, and since it's fully transient, solving for 5 hours of physical time, it actually takes about 8 days on 200 cores. So it's not a cheap computation. And that's also why drift flux is important. Doing this with like existing Euler methods may take months.
Can I ask you what's the rough size of the mesh in the core compared to the overall diameter? Do you have that information?
Excuse me again?
The size of the cells in your mesh compared to the diameter? Or
okay, so the diameter of the whole tank is 42 meters, and the smallest cell size at the bottom, because I have to resolve the boundary layer, is 3 millimeters.
Okay.
So it needs a steep grading and some meshing techniques to reduce the overall cell size, because it's obviously not possible to resolve millimeters in a tank which has 5 milliliters.
Okay, no, thank you very much, Daniel. We're coming up to the end of our 45-minute session with 25 seconds to go. So all I will say is that, well, thank you very much to the 3 presenters for preparing those presentations and for the interesting work that you've been reported on. And if there are any other questions to come, I'd urge you to continue the discussion with the individual authors through the discussion forum that's on the portal. And thank you again for this.